Hi, welcome to week 4 of social network analysis. This week we'll be looking at community structure within the network. First, we'll explain why community structure is interesting. Mostly it has to do with, instead of one big hairball, you have different regions within the network that are interacting within that structure more than they are with the rest of the network. So that's going to give you some information about what is actually going on besides, oh my gosh, everything is connected. Next, we're going to look at different definitions. How exactly do you define that this set of nodes is a community as opposed to this other set of nodes maybe is not? And finally, we're going to look at, given a network, how can you detect the communities within it, and how can you evaluate how good that those extracted communities are according to some criterion. So first, why do we do it? And I'll go through 3 separate reasons. The first is, well, these reasons are kind of social network specific. So the first is you can discover communities of practice. If you have communication between individuals, discovering which groups of individuals tend to communicate more with each other can tell you what is the structure of collaboration. So in a study done at HP, what they did was they took all the email communication, organically found what are the communities, and then they compared it against the actual reporting structure. So here gray is email and black is the reporting structure. And they found that in the vast majority of cases, the different communities, the communities just corresponded to the actual reporting structure. So if people were within the same unit of the organization, they had similar tasks, similar goals, and they tended to collaborate with each other. Okay, fine. This is a validation, right? You only looked at email communication and you applied your community detection algorithm, and what was spat out was totally reasonable. You got the actual organization back, which is informative. You can imagine doing the same study in an environment where there is no formal organizational structure, but you still want to know how did the individuals organize together. And this could tell you. What was particularly interesting in this study was that there were a few communities that were detected which tended to cross different organizational units. And so when the authors of the study, Joshua Tyler and others, went and interviewed those individuals, what they found was that they had tasks which in fact bridged different parts of the organization. So for example, printers with new networking functionality. Well, you needed the printer hardware people and you needed the people who know about networking. And so in a way, the community detection was giving a more accurate picture of the current collaboration structure than kind of the formal organization, which may or may not have caught up later, for example, by doing a reorg. This next example is a very, very classic example of the Zachary Karate Club. This sociologist, Zachary, was studying the interactions within a university karate club. And he said, well, who do you talk to regularly? Who do you like? Blah, blah, blah. And he got this social network. Well, while he was studying that karate club, there was a little bit of infighting with individuals in the club, and the club split in 2. The question is, given who was talking to whom and who liked whom, could you have predicted which way the club was going to split? And if you can, this is kind of a test for whether your community finding algorithm is good or not. Then that's useful. Imagine if you can look at any social network and you can say, well, if things get tough, I think this subset is going to go. So that seems useful. This next example is taken from the book. It's actually kind of a Payek manual that teaches you a lot of social network analysis as well. It's called Exploratory Social Network Analysis with Payek. And in this particular data set, which I've now remapped with Gephi, you have workers at a sawmill, that is, they're processing wood. And there are different kinds. So here you have the management. You have English-speaking workers, they're marked with E, and then you have different roles. So the Ys work in the yard, the Ps are the planers, and the Ms are the millers. And what happened was that the management wanted to introduce a new plan. And they thought that everybody would be on board because it was supposed to be beneficial all around. What they found instead was that there was a lot of resistance from actually the Hispanic workers. They called in a sociologist who mapped who talked to whom frequently. And after mapping everything out, said, I think you should talk to Juan. The management talked to Juan, explained the plan. Juan said, I will talk to my friends. Next day, practically everyone was on board with the plan. So the quiz is, why did this happen? What is it about the structure of this network that would have told you that talking to Juan is the correct answer, the correct thing to do? In this final example of the usefulness of community finding in social networks, we'll look at opinion formation. So what I'd like you to do is to actually go to this link. Let's see if I can find it as well. Hopefully. Okay, so here you have two choices. You can either create a network that has community structure, and you can lay it out a little bit more so it's more clear, or you can turn community structure off. So I'm going to create an Erdos-Renyi graph instead, and then you can do something called update opinion. And what happens is that each node looks at two of its neighbors, and in this case it's changed its opinion, it's turned into a square. And what it does is if a majority of its neighbors have, say, the red opinion, it will switch to red if it isn't red already. If it's equal numbers of red versus blue, it'll just flip a coin and it may switch or it may not. So I'd like you to do this repeatedly for the Erdos-Renyi and the two communities and see in which case you can have divergent opinions persist in the network in the long run. That is, you do a lot of updates of the opinion, and sometimes, though not always, different parts of the network will maintain a different opinion. So let's try and go back to PowerPoint. Excellent. Okay, so this is your quiz question, which I'd like you to answer. So hopefully what you saw was that when you have two separate communities, because individuals can have more ties within the community than outside of the community, they can actually, they're seeing like-minded individuals and they can persist in their opinion even if, say, the rest of the network is thinking something else. They're just not evenly mixed enough such that they would be influenced and the opinion would propagate throughout the network. So in this final example, it's a high resolution map of science that the researchers did in a very clever way. They looked at access patterns in online repositories of scientific articles, for example, JSTOR, or actually scholarly articles. The JSTOR has a lot of humanities and social sciences, and natural sciences, it's mostly on the biology end of things. And what they did was they looked at, if you access an article in this area, what other areas are you likely to be exploring within the same browsing session? And if we look a little bit in greater detail, you can see things, for example, plant biology being closely tied to ecology and biodiversity and environmental science. And what's more, you can then collapse these different communities into metanodes and see how the metanodes are then themselves related to each other. So pretty neat applications of community finding. And in the next segment, we'll get to the more difficult work, although still fun, of trying to define what exactly are these communities. And then in the third segment, we'll look at how do you actually find them. Now that I've hopefully convinced you that finding communities in a network is a useful and noble endeavor, let's see if we can figure out what a community really is. So, what makes a community? Perhaps it's mutuality of ties, so that everyone within a community has edges to one another. Maybe we don't want to be so stringent. Not everyone has to have an edge, but everyone should know at least K other individuals within the community. That's what makes a community. Maybe we're more interested in information flow. So for what we may want is that everyone is reachable from anyone else in a short number of hops, and we determine what that number is. And finally, maybe we don't want to set that it's, K other individuals that you know, but just that you know a certain proportion of individuals within the community. Okay, so before we get started, I think a very important point to note is that part of the reason why we see this community structure is because it arises out of a bipartite structure. A bipartite network is one where you have two different kinds of nodes. Say these are all individuals and these are all events. And so then you link all individuals who went to the same event together. So for example here, the first 4 individuals went to this first event, and that puts them in the same clique. For example, if the edge signifies did 2 individuals attend the same event, and this could then be embedded in communication frequency, etc. So yes, they probably all communicated because they went to the same event. So when we go about this task of discovering communities, what we may actually be finding are the different contexts, whether it's events or affiliations in clubs. For example, for boards of directors, do the directors sit on the same board? Well, then they're linked in the director network. So it's something to keep in mind, right? That this one mode representation of who talks to whom, in this case for social networks, is really an embedding of sorts of a more multidimensional network that exists out there. And so we're recovering some of it by doing community finding. Let's look at the first definition, that everyone should know everyone else within the same community. This is the definition of a clique. It's a fully, completely connected subgraph. And when you look at the cliques, they can overlap. So here we have 2 cliques, each with 3 members that happen to overlap. Within the clique, everyone knows everyone else. It's just a closed triad. Here we have a clique of size 4. Again, each of these 4 individuals knows the other 3. Let's go back to that community structure we saw in the opinion formation example and see whether we can figure out how common cliques are within networks with community structure as opposed to the equivalent Erdos-Renyi random graph. So we can find it. Okay, great. So here we are, and all you're going to be doing, I guess not that. Okay, we're going to set up here, and we're going to, you can lay out the network, and then we're going to highlight the maximal clique. So here's the Erdos-Renyi version. So we can set up some more, highlight the maximal clique, or we can see the familiar community structure and again look for a maximal clique. And you can click this multiple times if they're the same multiple cliques of the same size. Okay, so that's your quiz question. And moving on. So how meaningful are these cliques? For one, they're not really robust. So let's say two people are not friends or didn't talk at the party or something like that, that invalidates that whole clique. It's no longer a clique, and maybe you then miss the fact that it's really a community. The second part is that maybe it's the clique itself is not that interesting because everyone's connected to everyone else. You don't have a densely connected core and then more peripheral individuals. All you have is that densely connected core. And there's no point in running any centrality measures on this because everyone has the same degree, any other centrality measure you would like to apply. And finally, how cliques overlap may be more interesting than simply the fact that they exist. And in the last segment of this week's lectures, we'll talk about a clique percolation algorithm that takes advantage of exactly this fact. So let's be a little bit less stringent. K-cores say that unlike cliques, you don't need to know everyone in your K-core, you just need to know K of them. So looking at this network then, can you tell me what is the K for the core circled in red, or depending on your quiz question, what is the K for the core circled in blue? Indeed, you should have found that this is a 3-core, so every node on this side is connected to at least 3 other individuals within that same 3-core, and the one on the left is a 4-core because everyone's connected to at least 4 others. What makes K-cores also not that robust is this example down here where you have a node that really should rightly belong with all the other nodes in this 4-core, but it has only 2 edges. And so it can't be part of a 4-core. It would need at least 4 edges to do that. And so the next core that it can join is a 2-core that then envelops both of these communities. And so we would incorrectly, really leave this one out if we were looking for kind of meaningful communities. Of course, if you want to stick to the definition 4-core or bust, then yes, that node should be left out. But is that really what you want to get out of your community finding exercise? As I mentioned before, sometimes you want to just look for potential for information to flow. In this case, we may just be interested in a set of nodes such that, for example, any node is reachable from any other node within two hops. And so in this case, these are two cliques because everyone can reach everyone else within just 2 hops. And there's some problems with this. The first is that even though 2 nodes, for example, these 2, may be reachable in 2 hops, that other node may be outside of this 2 clique, right? And so the actual diameter of this 2 clique is greater. Actually, it's this one. It's diameter 3, right? The longest path between any 2 nodes is called a diameter. And here, it's actually larger than the n of the clique. And it's also not so great that we've left this node out. So these n cliques can also be somewhat funny animals. The final definition we'll examine are p cliques. This is where instead of saying you have to know k of the other individuals, you have to know at least the proportion p of the individuals within the cluster. So all of these methods that we talked about really focus on networks that don't have any sort of distinction between the edges, so all edges are weighted equally. this is kind of the minimum information scenario. And you're actually better off if you know how frequently individuals communicate, because very likely those within the same community are talking more often. And so if you're lucky, you can actually just use this information directly. For example, you could eliminate ties that are not reciprocal. So going back to the dining table partners data set, you could just say, well, if two girls did not reciprocally name each other as someone they wanted to sit with at dinner, well, then let's toss out that edge. And that will reduce the network, and you'll be able to see more coherent communities. Another thing that you can do is just keep all the edges above a certain threshold and throw out the rest. So that's what I'm going to attempt to do now in Gephi. These are political blogs from a long, long time ago. I was studying these, and let me just try and fit all of this on my screen. Great. So I sort of artificially removed the weights and any sort of partition just so you can see that, and of course, if this wasn't laid out, you may have trouble seeing that there are two communities in here. In any case, this looks very densely connected, and it's not that clear that, these kind of clique algorithms, they would probably lump everything together because it is just such a dense network. All of these political blogs were mentioning each other left and right. But let's see if we can tell left and right apart. So what I had done was sort of artificially remove the weight. So what I'd like to do is move the mentions into weight. So I want to take mentions and copy data from mentions into weight. Okay. Hopefully that worked. So if we go back to overview, great. So now we can see that, in fact, what we perceive to be the two communities, and actually let me color them now. So you have the conservatives and the liberals, and you in fact do see that the conservatives tend to talk to each other more often, and the liberals tend to talk to each other more often. And now we're ready to apply a filter. So I'm going to do that. And we can increase the filter. So for example, maybe they have to have mentioned each other at least 4 times. And this already thins out the network a lot, but still you have most of the liberals connected, most of the conservatives connected. If we increase this a little bit more, a little more, come on. Okay, for the most part, with the exception of, let's see who these people are, Talking Points Memo and Whizbang blog, who mention each other a lot. For the most part, you see 2 separate communities, and I didn't apply any sort of community detection algorithm, no cliques, no K-cores, no nothing. All I did was threshold the weights. But in the next segment, we'll be talking about what you can do when you don't know the number of communities there are, whether they will be cliquish or not. How can you automatically, in a systematic, principled way, discover community structure, especially in large networks? So that's what we'll do next. In this last section on community finding, I'd like to discuss how one actually goes about discovering communities in networks. We talked about how simply looking for cliques or K-cores, etc., how that can be a little bit arbitrary. What if we had a criterion that said, once you've partitioned the nodes into these groups, so the key word is, for now, is that we're partitioning, we're chopping the network up, that we can say that this is the optimal way to chop the network up with respect to some criterion. And these would be the natural communities that exist in the network. The trick is just to find them. One approach is hierarchical clustering, where you compute some similarity between the nodes, and you, to start with, each node is in its own component, in its own community. And then you find the two nodes, for example, that are most alike. And this similarity could be things like how many neighbors do they have in common, or if you have a weighted network, how often do they communicate with one another. Regardless, you have some notion of these two nodes are close, they're similar, and you start agglomerating in this way. And there are, of course, some decisions you have to make. Do you pick the node that has the minimum distance to a node in the existing cluster, or do you look for the average similarity being the highest, etc., right? So there are different options in hierarchical clustering, but one nice thing is that as you're aggregating up and up, you can, and finally you have the whole network is in the same component or same community, you can then decide at what level you would like to cut. And so depending on how low you go, you have very refined community structure or very coarse community structure. Now, there is a very efficient and successful implementation of this in Payek and some other software. To my knowledge, it's not implemented in Gephi, and I've looked a little bit at iGraph and NetworkX, and of course, these are things that you can sort of implement yourself if you're a programmer. So let's leave hierarchical clustering for now. It is definitely an okay way to approach finding communities and networks, but it doesn't necessarily fulfill this criterion of we have some single metric that we're trying to optimize, right? Hierarchical clustering is just more organic. We're going to keep lumping together nodes and groups of nodes until it's all lumped together, and we're just going to somehow decide where we want to stop, but we don't really have that stopping criterion yet. If we go back to the Zachary Karate Club, I just wanted to illustrate what this might look like in Payek. So if you remember, this is the club that broke up, and we just wanted to see what would a community finding algorithm have predicted would happen, who will go where. So I had somehow managed to accidentally delete the last part of this lecture, so this is a little bit of a redo, so apologies for the disconnected flow. Where I was at was looking at hierarchical clustering in Payek for Zachary's Karate Club. That is, can we predict that these folks are going to go one way and the rest of these folks are going to go another? Before we do that, we're going to look at the adjacency matrix in a pretty neat way. What I've done is I've used Payek to color each entry in the matrix where there's an edge as black. And you can see the way the data was originally entered already betrays some structure. However, it's not very clear how many different communities there are. If we were to randomly permute the rows, we would get, so this is the same network, it's just that which vertex has the label 13 and is in the 13th row is different in this matrix than it was in the previous one. And here we can see very little structure, right? This is a random permutation. After we perform our hierarchical clustering, we can repermute the matrix such that those nodes that are in the same cluster are placed close together. And now we can see clearly that there are two distinct communities, each with one or two very central individuals. One other form of output is the dendrogram, which tells us as you join nodes and groups of nodes together that are similar in this hierarchical clustering process, you can see which nodes are in the same group. And eventually you end up with just two groups, which then you can compare. Are these individuals the ones who split off? This next way of clustering the network was proposed by Mark Newman and Michelle Girbon. And it's very computationally inefficient, but it's also quite intuitive. So I'll cover it just as a way of building our intuition and also using this approach where we're allowing the clustering algorithm to work on its own rather than saying, oh, there must be a clique, and then just having different stopping criteria, just like we did with the hierarchical clustering in Payek, where we had vertex similarity deciding who's going to be joined. In this case, we're going to be starting with a complete network and we're going to be taking edges away. So we're going to be deconstructing it and getting finer and finer grained communities. Now, the basic idea behind this is that there's some edges that have high betweenness. Edge betweenness is, really the same definition as node betweenness. It just counts the number of different shortest paths that pass through an edge. And if an edge has high betweenness, that means it's between different sets of nodes. So removing that edge might then reveal what these different sets of nodes are, because it might actually, if you keep doing this, disconnect those communities completely. So say we have a network such as this one with two fairly clear communities, we might expect that these edges in between here are the ones with high betweenness. And what we're going to do is we're going to iteratively find the one with highest betweenness, remove it. Now we recalculate, and this computation is expensive. That's why this algorithm is slow and doesn't scale to really large networks. But we'd find the next one, remove it. We'd find the next one, remove that one. And by doing this iteratively, we get successively finer and finer communities. For example, first, in this case, separating out into 2 disjoint communities, and then 4 smaller ones plus 2 kind of nodes which become isolated. And if we evaluate this algorithm, we find that for the Zachary Karate Club, at least, there's only one node which was miscategorized. And, who is to say that this wasn't a more true affiliation for that node, but for whatever other factors, it went the other way when the split happened. The problem with hierarchical clustering and with this betweenness community finding algorithm is that there isn't a clear stopping criterion, right? It's great that you can stop at different resolutions, but how do you know which one is optimal, which one might be the true community structure of the network? So Girbon and Newman went back and they formulated this measure of modularity, which is going to tell us, at some point, we're going to maximize this quantity. And when we do that, we're going to have the most edges within the community, much more so than you would expect at random with this particular community partition. So what we do is for each node, we assign a community C. So vertex V is in community C sub V, and vertex W is in community C sub W. And now this is just a delta function. So this is going to be 1 if W and V are in the same community, and it's going to be 0 if they're not. So this function is going to sum just over the nodes which are assigned into the same community. And really this is algorithm agnostic, so you could be doing the betweenness clustering, you could be doing hierarchical clustering. It doesn't really matter. You can always calculate the modularity. So the question is, if V and W are in the same community, how many edges do we observe between such nodes in the same community? So we're just going to sum over the adjacency matrix, and then we're going to subtract how many edges we would expect at random, because C and W have degrees, so V and W have degrees, so K sub V is the degree of V, and K sub W is the degree of W. And so just by chance, these two may have linked to each other. The higher their degree, if they're two really large hubs, there's relatively higher likelihood that they'll be linking together than if they each have degree 1. And so that's just what we're doing. We're looking at the actual number of links within the community versus how many links you would expect based on the degree of those nodes that have been assigned to the same community. And we're doing this for all pairs of nodes. And for a random network, there would be no difference between or actually also for a random community assignment, there'd be no difference between what you observe and what you expect on average, and so your modularity would be 0. So an algorithm that can then use modularity is, again, a hierarchical approach where you start with all vertices as isolates. But now, rather than joining together vertices or groups of vertices that are similar according to some measure, we're going to join the ones such that the modularity increases maximally. And so we can keep doing this until the modularity no longer increases, or we can actually go beyond that point, allow modularity to decrease, but we still have a way of kind of minimizing that decrease and also getting larger communities. So this is very scalable up to very large graphs, and there is code available if you want to just download it standalone, but very nicely it's also implemented in Gephi. A reminder of why you may want to do this, here's some work, again, by Mark Newman, where he looked at, I think these are the scientific collaborations at the Santa Fe Institute. And rather than looking at, oh, there's this big network and everyone's working on something, you can find groups of researchers who are working on the same thing. And then you can even do something like visualize the metanodes, where one metanode represents everyone in the same community, and now you can start to see the relationships between these different groups. In this case, it would be how different groups of researchers cross-collaborate. One thing that I haven't mentioned that explicitly so far is that for the algorithms I've mentioned, we're really partitioning the network. We can't have one node be a member of two different communities. However, in a real-world network, this is hardly the case, right? When you looked at your Facebook network, you may have seen distinct communities. However, you have to be aware that that was a slice. That was a slice of that individual's network that pertains to you, and they probably know you through a single context, or at most two contexts. So that's someone you know from school, that's someone you know from work. But each of those individuals has lots of other contexts, so their other school or their other work that's not related to you, and this gives a very dense interlinked structure that's very hard to partition in the way that a lot of these algorithms would like to do it. And Yuri Leskovitz and his collaborators at Stanford have found that for many large social networks, the huge ones, precisely the ones that you would really like to be able to partition so you can study little parts of it, it's almost impossible to do so. So networks such as Flickr, Orkut, the Microsoft Instant Messaging graph, none of these are easily partitionable. And they found that at most, communities of 100 nodes can be separated, and everything else is too overlapped to do it. So what comes to the rescue then are community finding algorithms which allow for overlap, which allow nodes to be members of more than one community. One such piece of software that allows you to find overlapping communities is Clique Finder, which you can download for free. The basic idea there is that you're going to roll cliques around. It's a form of clique percolation. You're going to see how many steps you can take when the rules are as follows. You're going to choose a certain size clique, say a 4 clique, that is 4 nodes who each have links to everyone else within the clique. And then at each step you can omit one of the nodes and add another one, as long as that step allows you to form another clique. And you keep doing that until you can't move any further. So for example, here we have these 4 nodes in a clique, and then we can leave this one out and and get this clique here, and then finally we can leave this guy out and get this clique here. And in this way we can get overlapping communities, which is very relevant for social networks. It's very relevant for biological networks, and it's just plain more flexible to find overlapping communities than to partition the network in a choppy way. So just to wrap up, what we've tackled this week is that large networks can be giant hairballs, and if we can identify distinct regions within the network, that can give us important insights. Are these functional groups within the cell? Are these areas of research within science? Are these individuals who are collaborating within an organization? Now, how we approach that discovery of interesting structure is partitioned into two different themes. The first one is that you're going to look for specific structures. For example, you're going to look for cliques or K-cores. But if the network actually doesn't exhibit this structure and it exhibits some other structure, this approach can be too rigid. So what we talked about now most recently, and what's been popular definitely in the past 10 years or so, is looking for more organic approaches which let the community structure show itself to you. And you can use methods or metrics such as modularity to see whether, well, first of all, to try to find that organic partition, but also to evaluate any sort of community finding algorithm insofar as did it place nodes in the same community in a way that had much greater density of edges within the community than from those nodes to other places, other parts of the network. Now, for the assignment, you'll be looking at ingredient networks. So here is the network of ingredient complements. These are things that go together often or that co-occur often. And here is, oh shoot, what's the sandwich called? The sauerkraut and corned beef and Swiss cheese. How can I? Oh, it's a Reuben sandwich, that's right. And I wanted to show you one other web application that isn't going to be part of your assignment, in part because I don't want to overload their server, but that I think is very neat and uses an information theoretic approach that I will provide the article for, and you can check it out yourself. I mean, I think that article is just testimony to the many different creative approaches, really fun approaches that people have taken to discovering communities in networks. So let me try and switch over to that site. Okay, so I'm going to load my network of substitutes, and I'm going to do the directed network. And I'm going to calculate clusters. Cool. So each one of these clusters now is a set of ingredients. So if I double click on this one, I can find that it's clustered chicken and turkey and beef and sausage and chicken breast together as ingredients that are frequently substituted for one another. We can also, for example, look at olive oil and find olive oil substituted by butter, substituted by applesauce. I didn't know this until I was doing the research, but I guess applesauce is often a low-fat alternative that gets substituted in. Now, let me see if I can find, there's a neat kind of subgraph. Explore subnetwork. Cool. So here we have the subnetwork of the most common substitutions. So it looks like maybe applesauce is common both for butter and oil, but not, as I said just a second ago, for olive oil, right? So maybe if you're putting in the extra effort to use olive oil instead of any old oil, you're also less likely to then go for the applesauce, which, you know, may be lower calorie, but maybe doesn't taste as good as olive oil. So with that, I'll close out week 4. I hope you have fun with the assignment, and next week we'll be talking about small world networks. So going back a little bit to modeling and understanding the structure of these networks. Where does the community structure come from, and what implications does it have for things such as diffusion of information or the ability of individuals to find information within the network. So see you next week. Okay, well, hello. Here I am with Igor Perisic and Sam Shah at LinkedIn headquarters in Mountain View. And what I'd like to ask them is how they first got into social network analysis. Igor already started this story, which predates LinkedIn, so I'll let him continue.
So I'll start again. The beginning when I started within social network was in 2003.
Cool.
So it's really like in the dark ages.
Yeah.
At that time, the field was more driven by consultants, and you had these views of small networks. I was playing in the world of enterprise knowledge management. And enterprise knowledge management was you search for documents that matter, for something that a task I need to do, and for experts to help me out. And the cool thing that we had is that within each document, we could create a semantic map. So I give you a ton of document back, but I give you how this concept had linked. So that was a nice visualization, right? On the other side, we have names of people that are experts, and we felt like, well, this is kind of static. I mean, I don't know who they are, because otherwise I would have directly reached out to them. I don't know how they related to one another. So we took that and put it in the same display, because we had interactions around documents. We had the shares that we have today, so we could figure out why these two guys or these two ladies were part of the expert that we retrieved back. And then it created a map. It created one of these social maps. So that for me was my aha moment. Whoa, because small startup, 40, 50 people, you read the map and say, yeah, that's right, that's exactly how we work. It did work.
Mm-hmm.
But that was a small group setup, 40, 50.
Uh-huh.
The company didn't make it, so we stopped doing this. Now it's way different. Now it's maps of hundreds of millions of users. But there the difference is that you get to play with the real society, and you can actually see how it's alive, how it changes. That's phenomenal.
Mm-hmm. So one thing I've been telling students is how it's different when you slice a small network and people can easily recognize, oh yes, these are actually the groups that work together and so on. I would imagine that with a large network, you have a lot of overlaps from individuals changing companies. Does it make the same amount of sense? Or do you need to slice it before you can really work with it?
I think Sam and I can talk about how many pixels are there on the screen? Certainly less than 180 million, depending on the resolution. So if I put a dot per member, or I put a dot per member on Twitter, on Facebook, on LinkedIn, well, you have the screen that's full. So you have to slice and dice it to some extent. Mm-hmm. Mm-hmm. And through that, you start getting actually the nice signal.
Yeah, I think a lot of the challenge comes in actually how you're going to slice it too, because we've run into these problems where you slice it in a certain manner and then you lose the information that you really wanted to look at. You need to slice it in a different manner. So you look at like LinkedIn in the Bay Area performs very differently than it does, say, in New Zealand. And looking at that is actually, and figuring out how you're going to slice it is quite a challenge.
Uh-huh.
And it's also lead to me, my background is stats. And in the old days, it was like the myth of the average man. There's an average person, there's an average date. Well, The average man is half female, half male. The average family is 1.5 kids. That doesn't exist. The slice and dicing makes me remind that there's not an average user. There's not an average thing that you look at. There are different aspects. There are students, there are job seekers, there are professionals, there are this, there are that, there are that. Facebook, you can have there are teenagers, there are early teens, there are late teens. They're all different.
Was that a jab?
No, definitely not. Definitely not. Actually, one thing that I noticed is that it's drastically changing. And I don't know if did we meet in 2005 at that Microsoft meeting on social networks?
I'm not sure.
They brought a bunch of researchers at that time, and they brought kids, 13, 14-year-olds, and they started saying, "Oh, I do this on IM, I do this on MySpace, I do this on the phone, I do this on that," and we were all flabbergasted. Well, what, you doing that on this? Well, and it was like you don't break up with someone on IM, you call them up, or you don't do this on the. I forgot what it was. These individuals are now our users, and we all benefit from the perception of prevalence of social networks. That it's not something, oh, I don't know what to do on them. It's almost inbred into their DNA. Whereas for my generation, I would go and look at my sister. What is a social network? Why this? What that? My dad. So that changes drastically. So it's not the whole ecosystem sort of adapted to it. What will be in 5 years? I don't know, but it becomes so much easier to deal with it. That people actually see what they want from it much easier than us telling them what they should look at.
And I guess there's kind of a two-part question. To what extent is individuals' behavior when they use a network such as LinkedIn different from how they might, or the same as what they might be doing when they're doing regular networking or hanging out? And also, to what extent, such behavior might inform the algorithms that you use in trying to facilitate those interactions? Do you try to simulate what might happen in an offline interaction? Looking at Sam.
Yeah, I mean, I think there's LinkedIn is a little bit different in that, it's your information is inherently public. It's just like, you're putting your CV out there. You want to be found. Like, that's one of our core kind of principles of having this identity on the web. So, like, when you have that kind of dynamic, things change, right? Obviously, people are much more conscious about what they want to present. And then they change their behavior, I think, and to kind of reflect that, which it would do differently, say, in an offline kind of setting. It's I don't know, it's hard to actually understand what people would do, like the differences between that and kind of offline. I don't think we've actually have a really true, crisp understanding of that right now.
But what about, not right now as we're recording, but in 2 weeks the students will be learning about Milgram's experiment and passing messages six times. I think it doesn't maybe happen naturally, but if LinkedIn would be a place where you might facilitate people actually navigating the network. To what extent do you see that, and what kinds of smarts things just kind of blow up, right? The number of friends and friends and friends.
Again, 2003, there were 3 startups in social networks: Friendster, Spoke, and LinkedIn. If you look at Spoke was about facilitating business transaction. I'm a salesperson. I want to sell to company X. I don't know anybody in company X, but who do I know that knows someone? So it's kind of similar to Stanley's experiment. Like, how do I get my message to that person? Well, I don't know who that person is.
Right.
In this case, you have the setup of who you're trying to target. I always felt that would be the most successful startup in that domain. Of course, it hasn't. So I was wrong. I'm fine with it. We have a couple of products that we're looking into. One, the Pathfinder, which is actually trying to say, okay, this is how we are interconnected between A and B. So making that path explicit and making you the choices of which path you want to go down in order to convey a message or do anything across the board. And it's slightly tricky because you have multiple hops to go through, multiple types of connections, whether you're directly connected to the person, whether you share a group with that person, whether you live in the same area. All of these sort of interplay differently within the algorithm. And we're still learning how to actually make that thing better.
So any previews? Not that you have to give anything away.
Nope, unfortunately.
No, okay.
But that's one of these
Yeah.
these cool things when you work in places like we were talking before. We do have the data to try things out.
Mhm.
Most of our ideas don't make it out because it's either it's extremely hard, or the signal is not there, or the iterations and it's going to take longer than we thought, and some do. And when those do, sometimes they're extremely surprising to us. We just launched 2 products, which we laugh about it every day now, which are extremely viral, and they behave virally differently. And to understand why is actually a very fascinating question to think about.
So tell me more. It sounds like you had something to do with this.
Oh yeah, so we did this thing called endorsements, where you can provide kind of a lightweight thumbs up, sort of, to basically on colleagues' skills and expertise, and what we really it's really interesting to see that kind of social dynamic and that diffusion kind of happen as people slowly get to, I'm going to go and look at my colleagues and figure out what skills they have, and actually go and say, okay, this guy, Igor's really good at stats, I'm going to give him that. And then what does that actually change Igor's perception, and how that actually spreads throughout the entire network. And that thing has been growing immensely, much more than we actually even anticipated. And people are really in tune to that kind of thing. Another thing that we...
So where do you get the expertise? So I've seen a little bit of this activity. But
Yeah,
Very
so
secret.
that's another.
Yeah, we're only for you.
Off the record.
Yeah, it's only for people that are watching this. No one else is going to know. So you can do a few things, right? I mean, I think you can look at their profile information and be like, okay, based on the descriptions, you can do some sort of tagging around that. There's a lot of things you can do also on the social network as well, to be like, hey, what do my friends know? What do my connections know that can basically drive what I know? And then you can also do the same thing about your company, your title. And you bring all those pieces of information together, and you can have a decent representation of what some skills someone might know, right? And it's obviously not going to be perfect, but then you present it to the user, and then they kind of go and refine that. And it's been wildly successful using that kind of approach.
Cool. So kind of friend sourcing expertise.
Yeah, sort of.
Yeah.
It's sort of like playing on the homophily thing. Like
Yeah.
people with that skill tend to sort of cluster together. On top of it, with a professional network, so you would have those connections,
Right.
and you let them, as you said, that source of data percolate up.
So I've done a little bit of research, though, on what people say publicly and what they say privately. Have you thought about that at all? Publicly I say Igor is an expert, but...
And privately, it goes back to one other question that you had a little bit earlier. The difference is that everything that you do on LinkedIn is tailored. I mean, it has your voice to it, and you identify through it. You're not anonymous. You're not using a weird kind of name on that. But it's really you with your name, and that, I think, affects what knowledge goes through the network. It affects how you express it, and it affects how you are not expressing some things, which makes it very interesting to sort of
at
infer
least
it.
for you guys, you might be able to make some inferences when people don't endorse, right?
That would be a yes. I would think I could think about a couple of algorithms for it. The little bit difference is that on your profile you get full control about what it is out there. So if I'm saying you're not good at something, well, you get to control whether you want to show it or not, which probably we won't, right? So but then on the other hand, a lot of the targeting that we have, or recommendations, could take that into consideration. Yeah.
Okay, so this was part one. You said there were 2 things that went viral.
The other one is we just launched a way for having richer content on the site. So normally you would have like a small, almost a network feed, which is about 140 to a bit more characters. And we give the opportunity to some individual to say, well, you're an influencer list. I mean, why don't you use a longer post? Almost like a blog type. And again, it's tailored to, it's keyed on your identity. And we asked about 140, 150 influencers to message. And these are from one side the Romneys and the Obamas today, to the Richard Branson, who's the most popular one, to the head of the World Bank, to a bunch of individuals that are whose opinion you might want to read from time to time, and you hope from them to get very good content for it. So that's another one. That now, well, you see this list of individuals, like we follow that person, to get access to their postings, and or to get dynamically access to their posting, because you can always go, it's public, but to dynamically hear that, to be notified, and that has a different way to progress through the network. Because I follow, let's say, you or him, then you see, oh, he's following him and her, or maybe I should check what they're saying, and it has a different way to diffuse compared to the previous one.
Okay. Yeah, sounds neat. So what's diffusing is the following,
Yes.
as opposed to this activity which you're still kind of curating. You're
Correct.
identifying. Cool.
But at the high level, if you look at it, a posting on an influencer, it's a follow. So it's something new. It's the follower, post, influencer. The other one is the endorsement. Oh, there's such a thing as an endorsement. What is it? I didn't know it was before. What are these skills things that I knew what I didn't know that was before? And they are both very, especially today, because it's been what, about 3 weeks, 4 weeks that we started endorsement?
Yeah, 3 weeks.
And an influencer is about a week. So today you're really seeing this thing explode through the network.
And I guess identifying influencers, you mentioned, maybe you can use these endorsements and so on. Do you actually? How does one do that?
As it always happens, sometimes we are wildly more successful than we thought we were going to be. So we were rather careful to create very well at the beginning. So we went through a high level of editorial review. So okay, there's going to be just a few of them. And there were a couple of things that needed to happen. One is that they were willing to actually do this posting, so it seems dynamic and not like I'm posting one every year. So that you have this mechanism. And then what we did is, well, let us get ready for that second wave. If it works well, let's figure it out. And there we use multiple signals to figure out who is a potential influencer within a network. Part of the signals that we were using is the skills map. Part of the signal that we're using is that people are sharing content on LinkedIn. What happens to that content that they share? People share content within the LinkedIn share button on the web. What happens to that content? Is some just being static, or is something else being picked up? So they were already acting like influencers without them really knowing that they were, because they had a crowd that would actually follow what they clicked on, what they acted upon.
Cool. So yeah, we'll be getting to influencers in a few weeks. So I remember you talking in Dublin a few months ago now about predicting where people are going to move next for their next job, and somehow also incorporating geography. So,
For example. The interesting thing that we had done these maps for the US. Now I'm invited to go to Dublin, so I go to Dublin and say, I don't have the maps for Europe. And unfortunately, we couldn't refresh them quickly enough. And even after the meeting, some individuals that were in the audience were part of the labor bureau of something in Europe. What we were doing is more like, well, from your resume, I know where you're working, I know where you're going to work. And from that, I can infer maps of, are you sticking to a certain region, or are you willing to get a job opening into another place? If you look at it, it says, well, the migration pattern in real life. And we used part of that signal to figure out which job I should recommend to you. It's one of the things that I wish we would do much more on LinkedIn, much more looking into this labor market. One thing that recently we talked about was this skill gap. How come some people are not employed when you have so many job openings? Is there a gap between the skills of what you need for this job compared to what you have? Another part is, well...
You take some Coursera classes.
No, that actually... No, seriously, that's one of the things that we were trying to figure out. Well, if there is such a gap, how do you provide that visualization to individuals. Say, I'm looking for a job X, and well, there's not that many job X on the market, but there's this job Y on the market, which is close to the job X. But this is the skills that you miss. How do I get these skills? Well, I can work on this, but I cannot get the job, so I cannot work on this. So how do I get it? Well, classes, courses, books, online this, online that, and provide a way to actually get that, or how to get into
Or
this
maybe
place.
you can discover step companies. So maybe you can't directly
Perfect.
go from
Say now,
company
wait a
to
minute, I'm going to
company.
mark that down. Yes.
Right.
Yeah, I think it was really interesting in the context of veterans, for example. Like we have, we were working on these things where, veterans come, they leave the military, they have a set of skills, but what skills do those map to in non-military contexts? And, what kind of radio operator in the military, what are they really qualified to do, and how can you help them get a job, which can more utilize kind of the skills they use in the military. And that was actually a really interesting kind of thing to look at and deep dive into.
So I guess there's still this question of the textbook social network analysis and then social network analysis that scales to the amount of data that you have. And Igor, you said a little bit about it. Is there anything more that the students might want to brace themselves for, once they're done with the class?
Yeah.
Play with all networks.
I think almost everything you read in the textbook will break down at scale. We've noticed that quite a bit. I think a good classical example of that at LinkedIn is we have this people you might know feature, which tries to go and find the relationships on the social network that you might form. And you might think, hey, I'm just going to go and look at second degree, close triangles, and figure that out. It turns out that's really hard to do when you have 185 million members. Actually doing these things at scale and actually figuring out these relationships actually becomes very difficult. And it becomes very humbling. What works at 10 million quickly breaks down when you get to 50 million or 100 million things. And you have to think of different kind of approaches to do some of this stuff. Some of it can be parallelized, but a lot of the stuff actually cannot. So you have to think maybe about approximations or other things you can do, or really put domain knowledge into the problem to really understand how you can get these algorithms to scale. Quadratic is not generally good for us.
But just to say that reading something in a book and going to a course still matters. It's still important.
I'm not saying don't. The theory is very important to understand, and then to basically understand the applications of it, and then to really go distill and deeper dive into these problems.
The way that I was viewing it is being a statistician, the background is a bit math. So I started as a mathematician, then a statistician, and I'm now doing data mining. And there's a fundamental difference between A, B, and C. And math is geared into the mathematical model. Axioms, theorem, lemma, everything is true or false to some extent. A statistician, nothing is true or false. Everything is uncertain. But you still use math as the tools that get you towards figuring out what is optimal and what isn't optimal. And you understand the methodology. Then you go to billions of data or millions of this, and suddenly even doing a median is very complicated. And you go back to the average. And you say, I know the median is better as a point estimate than the average, but hey, you know what, I can only do an average fast enough. So I have to live with it. But then at that point of time, what you do in the back of your mind, you know what is the fundamental assumptions of different techniques. And you can use them and tweak them a little bit. So you're not doing the perfect thing, but at scale you have no options. But you know what is the impact of the change. And you can maybe correct for that bias or not. Because then at one point of time, the data is just way too big and way too much.
Cool. Well, so those were some of the challenges. Anything else that we may have missed?
There is beauty at scale. It's not, we shouldn't be afraid of scale. It's really fascinating to see things that when they have ton of traffic, because it gives it its dynamism, it gives it its diffusion signal to it. And because it's at scale, the other beauty is that it's hard. And because it's hard, it's interesting. So it's a challenge that people should pick up and not be afraid of. There are tons of things that would fail, but it's a very, very fascinating thing to play on.
Yeah, I think the other thing is to add to what Igor says, you can learn different things at scale. Things that, with a small amount of data, it becomes very difficult to understand, but when you have a large amount of data, say that LinkedIn has, you can see patterns that you would not necessarily see, which is actually, I think, very interesting to kind of go and play with.
Mm-hmm. Mm-hmm. Right. So really large things under the microscope.
Yeah, exactly.
Yeah.
That's a good way to put it.
And the other thing, these are fascinating times to play within that area.
Mhm.
Some years ago, even if you had the thought of doing it, you couldn't, which is why Friendster failed. And it's the right time to actually, it's a new door that's opened up into what we can think about.
Cool. Well, maybe we can end with that. Thanks very much,
Thank
Igor
you.
and Sam.
Thank you.
Thanks.
Thank you.